Okay, let's start. Good morning. So this week and the next, things are going to get rather more abstract. We're going to cover this the axiomatic definition of a vector space, and I'm going to give you more examples of vector spaces that are not necessarily like this. That's one. The other point that we're going to focus on is relativity, let's say. So we're going to be focusing on this notion of a basis more. And instead of immediately saying, for instance, that a linear transformation from Rn to Rm is nothing but a matrix of dimensions m by n, we're going to be really incorporating this idea of a basis between this correspondence between matrices and transformations, and likewise matrices and vectors and so on. So we're going to do all those these two things for the next 2 weeks, and it's going to be part of the second midterm. But before going into that, I thought it would be a good idea to spend some more time on this rank-nullity theorem and think a little bit more about these column spaces, null spaces, and so on. So just to remind you, so let's say that we have a linear transformation from Rn to Rm, and we attach to it two subspaces. We said we have one column space, right? And we denoted it like this. And here's the new symbol. I'm using this to represent that this thing is a subspace here. Okay. So this means that the left-hand side is a linear subspace of the right-hand side. This is as opposed to this other symbol that we were using. Recall that we were using this. That was like a point. It's a different type of containment. So the picture for this, you should have in mind is something like this. So you have this larger blob, which is R, and in it you have this smaller blob, which is L. Okay? If you were looking at, let's say, L in L, this really means you have this blob that is L, and lowercase l is a point in it. Okay, so this is sort of the distinction. Of course, this is just so that things are faster to write down. Should I go over the definitions of these, or should we just discuss some examples? Because I want to go through some examples that are in the book. I can just state these the definitions of these, but what do you think? Do you think it would be useful? Yeah, let's focus on examples then. Okay. So, however you define column space and null space, remember I told you that there are two more subspaces that are important, namely the so-called row space of A, and this is just a column space of A transpose. Of course, the columns of A transpose is the same thing as rows of A. And the final one is left null space. And left null space of A is nothing but the null space of A transpose. Okay? If A is going from Rn to Rm, column space is going to be here. Null space is going to be here. Okay? But then A transpose is going backwards, which means that the row space is going to be here, and then the left null space is going to be here. Dimensions of these four spaces we call rank and nullity. So, rank of A equals the dimension of the column space of A. Nullity of A is the dimension of the null space of A. Now, the dimensions of the row space and the left null space, they don't seem to have a specific name. So I can just call it the rank of A transpose and nullity of A transpose. Okay, so these are 4 numbers. Now we had this rank-nullity theorem. Do any of you remember what it says? Rank and nullity theorem. It tells you something about how these numbers relate, for instance.
The sum of them is the number per dimension.
Exactly, yeah. So now let me restate it. Now I'm going to incorporate into this these 2 numbers as well. So rank nullity theorem is the same thing as a fundamental theorem of algebra, linear algebra. Okay, so this is also called the rank nullity theorem. Okay, so the first step says this. The rank and nullity of A, so when you add them up, you should get back the dimension of the input. So n should equal to rank plus nullity of A. And the way I think about it is that this is the dimension that A collapses, right? It's in nullspace, and whatever is left is the rank. So it's a dimension that is it's a dimension of the vectors that survive. But I can do the same thing with A transpose, which would give me M equals rank of A transpose plus nullity of A transpose. Now the third piece is where things get slightly more interesting, and it is that this is the same thing as this. Okay? And so you can call this the column rank if you want, and this is the row rank. These 2 numbers, rank of A is the same thing as the rank of A transpose. This really is the new addition to what I have already stated regarding this fundamental theorem of linear algebra. But this is very useful, especially when it comes to dimension counting. Having these 3 equations is very useful. And I think in the last problem set, there was a problem where I was asking you to list echelon forms and so on, and then take transposes of them and compute the ranks of the transposes and so on. And I hope you discovered that this is indeed the case. Just so that we're clear, let's do an example with the 2x3 matrices. So let's say reduced echelon forms of 2x3 matrices. And let me write here reduced echelon forms of 3x2 matrices. Okay, we've done this a couple times already, but I think it is very instructive. So we start like this, then you have this, or this, or this. This is the end of it. I can modify it like so. Or I can modify this in two different ways. Either it is like so, or it is like so. Okay? And so here are the staircases. Now recall that we said that this rank, that is to say, the dimension of the column space, is the number of pivot columns in the reduced echelon form, which means that this has rank 0, no pivot columns, rank 1, rank 1, rank 1, rank 2, rank 2, rank 2. So this is like rank 0 piece, rank 1 piece, and then rank 2 piece. So let me, didn't break. So this is, this has rank 0, and so is any other matrix whose reduced echelon form is that. Any three reduced echelon forms in this middle piece has rank 1, and so does any matrix that can be row reduced to either one of these. And these reduced to, so these have rank 2. And using the rank-nullity theorem, okay, so these are going from R3 to R2, which means that nullity should be 3 minus rank. So this is 3, this is 2, this is 1. Okay? Let's do the same thing with 3 by 2. So now I have 3 rows and 2 columns. So this is how I start. Then I can have this, or I can have this. This is the end of it, or I can modify it like so. Let me draw the staircases. Now note again that this decision tree, if you want, is separated into ranks. Number of pivot columns is 0. Okay, I don't have any pivots. Pivot columns is 1, 1, and here I have 2 pivot columns. So rank is 0, 1, 2. And likewise, again, I can use the rank-nullity theorem to discuss the nullities. This time, well, I can use either one really here. But the point is that this time the inputs have 2 dimensions, which means that nullity now is going to be 2 minus rank. Okay, so any questions about any of this so far? Okay, so now let's do this. Let's start with each of these, and let's take the transposes of each of these. Okay, so right from the get-go, we have 7 matrices here and 4 matrices here. Okay? But that is not a contradiction, because just because a matrix is row reduced doesn't mean that its transpose too is going to be row reduced. Okay? So taking transposes. We have these. Okay, and then this is this. You see, this is not row reduced anymore. We have this. And recall that in our notation, the star means it's a number, but you don't know what it is. It could be 0, it could be non-zero. And then I have these ones. Write it here. 0, 1, 1, 0, star, 0, 1, star, and then 1, star, 0, 0, 0, 1. Let's now row reduce each of these to figure out to which matrices these correspond to. Right? Clearly, this is already row reduced, so there's nothing to do here. But this isn't. What I can do, though, I can take this and put it in the first one. Right? So let me write it like this. So this is row equivalent to this matrix. 1, 0, 0, 0, 0, 0. This is row equivalent to the same matrix. You see, I can take this, and whatever this number is, I don't care. I can always use this to get rid of this entry. And then I can swap things to get this again. Oh. And likewise here. This is already at a very nice position. I can use this to get rid of this entry and this entry. Here, again, I can use two swaps if you want. Take this here, this here. And likewise, I can take this to get rid of this entry, no matter what it is. And I can take this to get rid of this entry. Oh, sorry, so one. And likewise here. I can use this to get rid of this, and then swap these two to obtain this form. So now the blues are really in reduced echelon form. And note that now this matrix still has rank 0. Each of these matrices still have rank 1. And each of these matrices still have rank 2. Okay? So when we applied transposes, this property of a matrix being row reduced, we lost. That wasn't the case anymore. But still, the rank was preserved. Not necessarily the nullity, because that's not what I'm claiming here. I'm claiming that when you take the transposes, ranks are preserved. So let me write it here. So rank 0, rank 1, rank 2. How about the nullities? Now this time, you see, so this is 3, for instance, here. The nullity is not preserved because I have 2 non-pivot columns. So nullity is 2. In this case, the rank and nullity has to add up to 2 because the number of columns is 2. Nullity is 1, and nullity is 0. Okay? Does this make sense? So could anyone give me a reasoning as to why it is the case that this does happen indeed? Like we sort of saw an example in the case of 2x3 matrices, but based on sort of like this schematic, could you sort of come up with an argument or some sort of heuristic as to why it should be the case that when you take the transpose of a matrix, the rank is preserved, has the same rank?
Is it because if you have a pivot column, when you transpose it, you're guaranteed to have that pivot column again, just kind of looking different?
Yeah.
But the nullity, you're not going to have the same number of input columns when you transpose.
Exactly. Or another way of seeing this is sort of like more perhaps graphical. So we're thinking of these staircases as going down, but it doesn't matter. You can either go this way or this way. The point is that there's only one step here. And certainly when you switch it to this version, it's still only going to have one step. Right? So that's sort of like a heuristic as to why it should be the case that the rank of a matrix is the same thing as the rank of its transpose. Okay? So keep these three in mind. It's very useful, I think, to be able to count the dimensions of certain things before even computing things. Okay? Now there's a third version of the fundamental theorem of linear algebra that says something about how these four spaces are positioned inside these vector spaces. But possibly we're going to discuss that once we start talking about inner product spaces. What we would really want to say is something like the column space of A and the left null space of A, that is to say the null space of A transpose, which are both subspaces of Rn as Rm, are really perpendicular. But we'll get to that later. Okay. Any questions about these so far? Of course, I could take these and take their transposes, and you're going to realize that the ranks are still preserved. Okay? Good. So let's do more examples. Well, that's because so to compute to find the vectors in the null space of A, you set up the equation Ax equals 0. So when you take the transpose of this expression, the transpose changes the order of the products, which means that when you take the transpose, you get this. So, so this is sort of, instead of feeding your vector from the left, from the right, you're feeding it from the left. And that's why you call it the left null space. Yeah. There are fancier terminologies for these, which we're going to discuss later. But this is also called the kernel. Sorry, this is the image, kernel, coimage, cokernel. Those are also names. But left really means that you really take the transpose of that equation there. And so you're feeding, instead of column vectors, you're feeding row vectors, and you're trying to solve this equation, is what it's saying. Does this answer? Yeah. Yes?
Where does
Say again?
What do they represent, the blue?
Reduced echelon forms.
Okay. Is it just rotating the rows?
From here to there?
Yeah, like how did you take the white one to the blue one? You just
Oh, yeah, it's interchange, for instance. Sorry, yeah, so I can swap these two, for instance. Yeah. Or, like whatever this number is, I can certainly take this, multiply it by an appropriate number and add or subtract from it to get rid of this entry, and then swap these two to get this. Yeah. Any other questions? Okay. Okay, let's do examples. So for instance, let's consider this. I'm going to start from a matrix. I'm not going to start from a system. Let's say that this is my matrix. 1, minus 3, minus 2, minus 5, 9, 1. So I'm thinking of this as a transformation, goes from R3 to R2. So if I wanted, I could write it as a transformation like this. A of x, y, z goes to x minus 3y minus 2z is the first entry, and then the second entry is minus 5x plus 9y plus z. Takes a triple, turns it into a certain pair of numbers. So let's compute everything. So let's first look at the column space. Now recall that the column space of a matrix was nothing but the span of its columns. In this case, because our output is two-dimensional, that means that the column space is either going to be 0, so it's a zero-dimensional space, or it's a line in the plane, or it's everything. It could be all three. Okay, so let's do row reduction. So that's a 9. So I'm taking 5 times the first row and adding it to the second one to get rid of this. So now this is minus 15, minus 6, minus 10, minus 9. Okay. Scale the second row. 0. So I want to have 2, 3. Okay, so at this stage, what I can do is I can take this and multiply it by 3 over 2 and add it to this to get rid of this. But then I'm going to have fractions. So let me scale this first row by 2 as well. And instead of doing something with the second row, let me do something with the first row. Let me make this a plus. Okay, so now I can just add without multiplying. So that's a 0, and then that's a 5. And this then becomes 1, 0, 5 over 2, 0, 2, 0, 1. So I'm dividing it by 6, 3 over 2. So we came up with the reduced echelon form. Recall that this reduced echelon form for any matrix was unique. So this is the unique reduced echelon form. I have 2 pivot columns, which means that the rank is 2. So let me write it here. So 2 pivot columns rank of A equals 2. Now I can at this stage go back and say, oh, the first and second columns are the pivot columns, so this and this gives me a basis. But I can also say this. Rank, or rather the column space of A is going to be a subspace of this. And this has at most 2 dimensions. This is exactly 2 dimensions. If the rank of A is the same thing, so if the rank of A is 2, that means that really the column space of A is all of R2. Okay? So I can certainly use the first 2 columns if I want it, or I can just say, for instance, 1, 0, 0, 1 gives me a basis. For the column space of A. Okay? It is 2 dimensions after all. I have everything. And these 2 really is sufficient, necessary and sufficient. Now, another way of saying the same thing is to say that this transformation is onto. Okay? AKA A is onto. Okay? Any questions about this so far?
Is the column space always onto for its dimensions?
What do you mean by column space onto?
So it says column of A goes to all of R of 2.
Yes.
And R of 2 is the dimensions of, or the rank.
Yes.
And it's the dimensions of the column space. And so I'm asking if the column space is always onto its dimensions.
Oh, I see. That is true. But so here's the thing. If, let's say, in this case, let's say that in this case, it turned out that the rank is 1. I could still say that the column space is, a one-dimensional thing. But the problem with this is that we started with a 2 by 3 matrix. So the output is 2-dimensional. When you write it like this isn't really telling you more information than this. This is just telling you that this column space is 1-dimensional. Because there are many ways of seeing this vector space as a subspace here. In this case, it turned out that this is everything. So in this case, it wasn't really that much of an issue. But in general, this is not a very good notation, I would say. You can say something like this is isomorphic. We're going to learn that word as well, probably next week. But so perhaps what you can say is that any linear transformation is onto its column space. Okay. Any linear transformation is onto its column space. Does this sort of correspond to what you were asking? Yeah. So at this stage, for instance, I can also say immediately that A is not going to be 1-to-1. Okay? Because if the rank is 2, by the rank-nullity theorem, rank plus nullity should be equal to 3, which means that the nullity is 1. So nullity of A is 3 minus rank, which is 1. If nullity is any number apart from 0, that means that your transformation is not one-to-one. Okay? Because it is collapsing certain vectors to 0. Really, it literally fails to send two distinct vectors to distinct places. Okay? So we can go further. I know that the nullity is 1, so that means that the null space of A is a one-dimensional subspace of the input space. But we can still try to see what it is. Come up with a vector that spans it. Right? So because the nullity of A is 1, we know that the dimension, let me say it like this. Null space of A in R3, using that notation over there, is 1D. It's a one-dimensional subspace. It's a line passing through the origin in this three-dimensional space. If that is the case, then certainly it must be the case that there's a vector that spans this. There's one vector that spans it. Let me write it over here. So, basis for the null space of A. Well, the null space of A is by definition all those vectors in the input space that A sends to 0. Okay? So that is to say, I need to solve A v, let's say, or A xyz equals 0. So, need to solve A xyz equals 0, 0. Now, certainly when I'm trying to solve a system like this, I can always reduce it, right? And the solution is going to stay the same. So I really have this. And let's use the augmented matrix notation. This is my augmented matrix for this system. Augmented and reduced, of course. Now, how can I read this back to get the expressions? Recall that this is x, this is y, this is z, this is the right-hand side. Now, the first row says x, so 1 times x plus 0 times y plus 5 over 2 times z equals 0. The second row says y plus 3 over 2z equals 0. Yeah, 3 over 2z equals 0. And it doesn't tell me anything about z. Okay? Now note that x and y are variables that correspond to the pivot columns, and z, this third column, is a non-pivot column, and that gives me the free variable. It is a bunch of numbers that I cannot do anything about. So z, free. So this would be the general solution of this thing. That is to say, any vector x, y, z in a null space of A would need to have coefficients x, y, z so that these are satisfied. I can't say anything about z, but there's a relation between x and z, and there's a relation between y and z. Going further, what I can do is this. This vector x, y, z, maybe I should write it like so. X, y, z is in the null space if and only if, right, this is equivalent to having these relations. So minus 5 over 2z in the first entry, minus 3 over 2z in the second entry, and z in the third entry. That is to say, this is nothing but z times a certain vector. Z is a number. Okay? So any vector that is in the null space of A is a constant multiple of this vector. Okay? If I wanted, I could have said something like, oh, let me finish this and then I'll go further. So let's write it over here. Thus, any vector in the null space of A is a constant scalar multiple, let's say. Scalar multiple of the vector B, and that B is going to be that vector over here. Minus 5 over 2, minus 3 over 2, 1. So I can safely say then that the null space of A is the same thing as the span of this vector. And certainly, any vector by itself, as long as it is the non-zero vector, is linearly independent. That means that the set consisting only of one vector, that is B, or the ordered tuple if you want, consisting only of B, is a basis for the null space. So B, let me just write it like this, is a basis for the null space. Okay? Any questions about any of this? So you see, now that I have this vector, I can also imagine how this null space of A looks like inside 3 dimensions. Already at this stage, when we computed the nullity, I had the knowledge that null space of A is a certain one-dimensional subspace of R3. That is to say, it's a certain line passing through the origin. But now, I also have a direction. It's this. In this direction, it is passing. Okay? Now, we're using here this instead of the basis, because it is not the case that vector spaces has a unique basis or a unique basis. Given any subspace, there are many bases for it. Okay. So let me say, for instance, I could do this. C, which is minus 5, minus 3, 2, is also a basis. For the null space. Okay? Certainly, if any vector in the null space of A is a constant multiple of this, well, this is also a constant multiple of it. Well, I can also write any vector in the null space of A as some multiple of this particular vector. And certainly this is also by itself linearly independent, so this too constitutes a basis. Okay? Perhaps you may want to prefer this over this because this doesn't have fractions and so on, depending on the situation. Okay. So for instance, here too, when we talked about a basis for the column space, I said immediately, oh, the rank of A is 2, which means that it is on 2, which means that the column space is everything. It is R2. So I can just take any basis I want. And of course, the horizontal and vertical vectors constitute the basis. And that's all good. If I wanted, I could just say the first column and the second column too constitutes a basis for the column space of A. Depending on the situation, one basis becomes more convenient over the other one. Now, as this week progresses, we're going to start talking about polynomials as vectors, for instance. And we're going to see, probably in the next problem set, we're going to see a bunch of different bases for polynomial spaces that are important in certain applications. Sometimes you use something called Chebyshev polynomials, for instance. And sometimes you use, let's say, trigonometric polynomials, Legendre polynomials. There's a bunch of different classes of polynomials that turn out to be bases for polynomial spaces. This is very important in applications because the fact of the matter is that given any application, there are certain calculations you want to make. And if you choose the right basis for the application, it turns out that your calculations becomes easier. And so that's sort of like a degree of freedom you end up needing to have for very application purposes, very important application purposes. Okay. Any questions? Yes.
So I guess a part of the usefulness of this is basically when you figure out the basis of A, you basically get to say, I don't really care what A is anymore because I know its bases are this, and so I'm just not going to think about that. I'm just going to think about the basis.
Well, basis of the column space or the null space of A.
Yeah.
Yes. Yes. So there's this other thing, right? So let's imagine you have a 15 by 75 matrix. So 15, 75. So that means that it is going from R to the 75 to R to the 15. Now, so you want to imagine the null space and the column space. But these are like higher dimensional linear subspaces. It's hard to imagine those. But when you come up with a basis for each one of them, and you can certainly, this is like an algorithmic procedure, now you have finitely many things to worry about, finitely many numbers. So you see, so you're reducing the complexity of the situation. So we're going to discuss more uses of the basis as well. So another thing you can do, for instance, and you've actually done this in previous problem sets, if you have a basis for a space, you can define a linear transformation on it by just telling how that linear transformation transforms the basis elements. Yeah. So that's also something that we're going to discuss. Any other questions? Okay. I think this is it for today. I'll see you tomorrow. Okay, let's start. Good morning. Today, finally, we're going to discuss this abstract definition of a vector space. And before that, I wanted to mention a couple words about problem sets. I understand that the last problem set was perhaps a bit rough. Part of the reason why that happened, I think, is because I ended up cramming topics from two different weeks into the same problem set. And then it got out of hand a little bit. I should say that, like if you, so of course, one thing that you should do is to start early. And another thing is that I have no issues whatsoever with discussing some of the problems that you haven't worked through yet. So you can sort of like look at a problem and you can sort of like feel like, oh, maybe this is going to take some time even to parse what is being asked. So I have no problems whatsoever if you wanted to meet and discuss before delving deeper into the problems. I should also mention that as this course continues, it's going to get harder and harder to complete the problem sets in shorter periods of time. So you're going to need to sort of start working on them early. Otherwise, it's going to be overwhelming. I am designing the problem sets to be that way. because math is something that you learn by, exposing yourself to it over a prolonged period of time. In any event, so here are the properties. So let me go back a little bit. So we start with this notion of a vector by this. I just said vectors are just elements of this particular space. I said any vector is of this form, v1 to vn are numbers, and it's a tuple, and I can think of it as a column vector whatsoever, so column matrix and all that stuff. But the point is that you can do two things with vectors. You can vector add and scalar multiply. I didn't discuss this explicitly at the time, but over time I think we have developed this understanding as to how vectors work, how addition and scalar multiplication works. And so here is the properties. And here u, v, w, 0 and minus v are going to be vectors, and c, d, and 1 are going to be numbers. So this box is all about addition, how addition operates. This box is all about scalar multiplication, and this box is all about how addition and scalar multiplication interact with each other. So for instance, this says that, if I'm adding 3 vectors, I don't need to worry about first adding these two and then this, because it is the same thing as first adding these two and then adding this. So when you're taking a linear combination, for instance, you don't really need to put parentheses. You can put 50 vectors, you can add them up, and you don't need to sort of like tell in which order you're adding things. Okay? And then here's another one. Certainly, you have this 0 vector that when added to any other vector doesn't do anything. Right? Next, if you have a vector, then there's another vector which is minus v. That gives you 0 when you add them. And finally, the order of addition doesn't matter. V plus w is the same thing as w plus v. So these are the properties of addition, and these are the properties of multiplication. Same idea, I can first take a vector, scale it by d, and this gives me a vector, and then scale the end result by c, or I can multiply these numbers in this number system that I'm using first, and then use this one number to scale this vector. And in my number system, for instance, I have the number 1, and when I scale this vector by 1, I should get back the same vector. And finally, if I add 2 vectors and scale, it's the same thing as first scaling the vectors and then adding. And likewise, if I add 2 numbers and then use that number to scale a vector, it's the same thing as scaling the vector using these 2 numbers and then adding the corresponding vectors. Okay? So these are straightforward properties for vector addition. And it turns out that as long as you have things, you have an addition, something like an addition, and something like a scalar multiplication that satisfies these properties, you have a vector space. Okay? You don't need to describe how the vectors look like. You can just axiomatically define what it means for something to be a vector space and what it means for something to be a vector. Okay? And so we're just going to take these and sort of abstract them out. And so I debated by myself whether or not I should do this. But eventually I decided to do it because I think everyone should should see this at least once. So we're not going to use these axiomatics for long, but still it's a good idea. It's a good thing that we see this. So axiomatic. Definition of a vector space. So before we started with what it means to be a vector, but really if you want to axiomatize something, you want to talk about the system of vectors. So you want to start with vector spaces, and then you want to say, oh, if I have a vector space, any element of it I call a vector. And so we're going to deconstruct these properties. And really, the deconstruction starts here. What I take as numbers. So there's an abstract structure called the field, and I'm not going to go into the axiomatics of that. I'm just going to say, let F be a field. So a field is just a mathematical structure where you can do addition, subtraction, multiplication, and division. Examples of this are real numbers, complex numbers. Certainly I can do the same thing. I can add, subtract, multiply, divide. Rational numbers, I can do the same thing as well. So these are the real numbers. These are complex numbers. These are rational numbers. And let me add one more. Let me call this B. These are the bits. So all four of these, and there are many more, of course, but let's just keep these as examples. And really, I'm only going to focus on this for the most part in this class. And each of these have different uses. So for instance, it turns out that whenever you have a phenomenon that involves rotation, it turns out that using complex numbers is much easier. Makes things much nicer. But of course, if you want to have some intuition, using real numbers is much more geometric. Or if you're worried about computation, for instance, using rational numbers, that is to say, numbers of the form p over q for integers, is much more simple to manage and store and everything. And bits, so this only has 0 or 1. And you can add 0 to 0, it gives you 0. You can add 1 to 1, it gives you 0. So that's the rule for bits. And so this turns out to be important in the context of information theory and logic gates and everything. Okay, but for now, I'm just going to use this letter F, but I really think R. A vector space over F. So I need to record, first of all, the field of numbers, field of scalars that I'm using, is, by definition, a triple. V, and let me say alpha and sigma. On purpose, I'm writing this in a weird fashion. After writing these definitions, we're never going to use this notation. Where V is a set. So it's a collection of bunch of things. I'm not even telling you what it includes. Alpha is a function from V times V to V is a function. So this is going to model for me vector addition, set of vectors. This is addition. And sigma is a function from F times V to V is also a function. Scalar multiplication. Maybe I should say vector addition here. With certain properties. I just want to take these properties and encode them using alpha and sigma with the following properties. So I should mention here, for instance, alpha of VW really models V plus W there. Let me say it's like this. Something like that should operate like this. And sigma of CV should really look like, or should really operate like CV. Okay. So now with this, let's encode all those properties. So I have properties for addition, that is to say for alpha. Right, so this box is for addition. This box is for multiplication, scalar multiplication, and this box for how they relate. So first property says, so alpha VW, alpha U. This is the left-hand side over here, for instance. So instead of V plus W, now I have this abstract alpha of V comma W, and then I put it in to another alpha. And so it should be some other thing. Turns into this now. So alpha UV W, that's the first property. Second property, now in the case of Rn, this was clear. Like what this 0 vector was, is it was clear. It's a tuple, all of whose entries are 0. But in the abstract setting, you want to state that there is such a thing. There is a vector, let me say an element, zeta, it's for 0, in V, such that alpha of B zeta equals V equals alpha zeta V. Now again, we need to abstract this out. In this case, it is clear what this should mean, but in the abstract setting, you want to say, given any V, there is something like a minus V. Because at this stage, we don't know what minus means. For any V, in V, there is a minus V such that, let me say V prime, such that alpha of V, V prime is the same thing as zeta, 0, equals alpha of V prime V. And finally, I need to say that it doesn't matter in which order I put these two vectors in to alpha, I should get back the same thing. Alpha of VW equals alpha of WV. So the box got longer and larger, but all of these really axiomatizes how addition, vector addition should operate. As long as you have an alpha like this that takes two things and turns it into one thing that satisfies these rules, that's something that I can call a vector addition. For the second box, I have a scalar multiplication over here, which means that now I need to tell things about sigma. So the first one is that if I do this, and then I do this, this should be the same thing as sigma CdV. What does this mean? This means whatever multiplication means in this F. And sigma of 1V should be the same thing as V. And finally, I need to say something about how addition and scalar multiplication interact with each other. So the first property says, this for instance, alpha of VW, sigma of C. So add V and W and then scale is the same thing as first scaling and then adding. And then finally, if I first add inside this field, whatever that means in my field, and then scale, it should be the same thing as should be the same thing as this. Alpha of sigma C B, comma, sigma D B. Okay? So number addition, and then I'm scaling it. So sigma of C plus D comma V is the left-hand side. On the right-hand side, I should have alpha of sigma CV and sigma DV. So that's it. Of course, we never think of vector spaces as like this. And once we have this abstract definition, we actually use these symbols, just like in this case, because that's the whole point of all these axioms. Okay, so these axioms are so that you can forget about the underlying sort of structure, and you can treat everything like this pretty much. Let me introduce one more thing. What is a linear transformation? Well, we had already discussed this axiomatic definition, recall. I defined what it means for something to be a linear transformation between vector spaces by telling how it operates, how it relates to addition and scalar multiplication. And so now I need to say the same thing with respect to alpha and sigma. Let V, and by this I mean this. So it's a set, it has an addition, it has a scalar multiplication, and W, it has its own addition and scalar multiplication, whatever that means again. A linear transformation. And while we're here, let's also increase our vocabulary a little bit more. Transformation operator, function, mapping, morphism, that's a fancy word, or even arrow, linear arrow. This is also a word that is being used. Is a function from the underlying sets. So from, let's say, phi v to w, such that if I first add two vectors in v, so let's say v1, v2, and apply phi to it, this is the same thing as adding the outputs in W. That's the first one. And second, I need to say something about scalar multiplication. If I were to scale a vector by C and then apply my transformation to go to W, this should be the same thing as scaling in W using the same number of the image. Okay? Now at this stage, we can, for instance, talk about already linear transformations, and pretty much all of the things that we've discussed so far apply, except that you don't have this useful tool of interpreting things as matrices. Okay? Everything is axiomatic, but many of the properties, many of the concepts generalize to this setting. I'm not going to keep writing these definitions in this more abstract setting. Let me just mention here that all the concepts that we discussed so far apply. all notions apply to the abstract setting. So for instance, a linear combination of vectors. Linear spans. Linear independence, or dependence, if you want. What else? Notion of a basis. Notion of a dimension. Null space, column space. What else? Transpose. Even when you don't have a matrix, there's a notion of what it means to take the transpose of the linear transformation. Transpose. What else? Invertibility of linear transformations. I can also define what it means for a function to be an affine transformation. Okay, everything applies to this abstract setting. Now, what is the point of having this abstract perspective? Well, the point is this, that when you're trying to use linear algebra, often things don't tell you that they are vectors, okay? You have a thing, and you have a similar thing, and you just realize that perhaps there is something like an alpha that you can use to combine these two things. And there is something like a sigma that you can use to take your whatever thing and scale it, in a sense. And so just because in nature there's no such thing as a vector space, at least at first glance, it becomes important to be able to identify things by how they operate. And more important than the definition of a vector space, really, the real thing is to be able to identify when when a transformation is linear. Okay? Often, whether or not some space is, or a bunch of vectors is a linear space, that's not a big deal. But if whether or not a certain transformation is a linear transformation, that's a big deal. Okay? Whenever you can realize that something is a linear transformation, appropriately interpret it, then you're in business. Okay? Now, I'm going to give more sophisticated examples later, but let's start easy, or rather relatively easy, and let's look at one of the fundamental examples of a vector space that we haven't discussed so far, namely a function space. So let's consider this. Here's an example. Let V be the collection of all functions from reals to reals. So this is a single variable, functions with real values. So V set of all single variable functions with real values. Okay, so maybe I should use the letter f, curly f, f for function. This is a function space. So any vector allegedly here is a function, okay? So any element in F looks like this. So I'm imagining in my head, it's like any point in this space is a picture. And what is the picture? It's the graph of the function. Okay? Is this a vector space? Certainly it is. Let me just tell you what addition and scalar multiplication is. Is a vector space. How do I add two functions? Any ideas?
By scalar or not? By adding to it?
Yeah. I have two functions. How do I add them?
You can just add the whatever you're adding to on the function, and then you can multiply the scalar.
Yeah, exactly. So if I have two functions, according to the axiomatics, the sum of them should also be a vector. That is to say, the sum of them should be another function. Well, so let me call h to be f plus g. And what is h of t, let's say? I need to tell you what h of t does. Well, h of t equals f of t plus g of t. I'm just adding entrywise or coordinatewise is sort of what they use. H of t equals f of t plus g of t. That's vector addition. And like your colleague said, if I have a function and if I have a constant, I have this new function, c times f. Let me call this h equals c times f. And h of t equals c times f of t. Now, when I plug in an input to my function, now f of t is a number, so I can certainly multiply these two. And whatever this end result is my new function. And that's going to be the scalar multiplication. That's how I'm defining scalar multiplication. Okay? So people would say addition and scalar multiplication defined entrywise or coordinatewise. So and scalar multiplication done coordinate-wise or entry-wise. Now, of course, in this space, we also learned, or you also learned possibly, that we can multiply functions, right? I can say f times g is a function whose value at time t, and I'm going to interpret this input as time, at time t is f of t times g of t. But that is not part of the vector space structure, okay? So that's something beyond. It's what's called the algebra. It's really an algebra of functions, but we're not discussing that. We're only discussing vector addition and scalar multiplication. We're not multiplying vectors, even though in this case it is available. We can do it. Any questions about this so far?
So this isn't necessarily linear then?
What isn't?
Like f and g?
No, exactly. I'm not telling anything about whether or not this particular f and this particular g is linear, differentiable, continuous, whatever. It's any function whatsoever. Certainly, these two properties are satisfied. I don't need any property for f and g in order for these to work. So, here are more examples. So now that we're done with these axiomatics, I'm never going to use this alpha sigma notation. I'm just going to keep using addition and scalar addition and multiplication, just like we were doing in the context of Rn. So first of all, this vector space is supposed to have a zero vector. What is the zero vector? Any ideas?
The function is 0.
Exactly. Exactly. So the zero vector in F is just the function. So let me say zeta of t equals 0. I'm just going to call it 0, of course. I'm not going to use like zeta and stuff like that. And let's try to imagine how this addition would look like. For instance, here's an example. Here's one example. Here's another example. Let's say that I have, let's say that F is this. Okay. And then G is this. This is F. This is G. Okay. So this is the function G, and this is the function F. If I wanted to write these explicitly, I would write it like so. I would say, these are, if you want piecewise defined functions, f of t equals, let's say this has slope 1. T, if t is positive, 0, right? It's a flat signal here. Otherwise, and here I can say g of t equals, well, let's say also this has slope -1. So this is, let's say, 0 if t is positive. And if t is negative, it is minus t. These are valid elements in my function space because I didn't tell anything about how the functions look like. I just told you that it takes the real numbers to the real numbers. So when I add them up, I can think of the addition like this. So imagine the graph of f and imagine the graph of g. At each point, let's say that you're looking at what is happening at t. According to our definition, you're supposed to take the value of f and add it to the value of g. So t is somewhere here, and t is somewhere here. Okay? F of t is t. G of t is 0. So somehow, because you're basically adding 0 here on the right-hand side, let's say, in the positive side, you're going to have this piece. And likewise, on the negative side, this is 0, which means that you're going to have this piece. In other words, you're going to get the absolute value function. Okay, so let's call this. So this is f plus g is the absolute value function. So I can write it like this. F plus g at t is the same thing as t in absolute value. Okay? So this is an instance of vector addition in this vector space. It doesn't look anything like this vector addition in the case of Rn because I'm not using numbers really. I am, in a sense, I'm using infinitely many numbers at the same time. But still, this is a valid way of vector addition. Let's look at another example. Oh, by the way, I should mention that these types of functions are very important in the context of machine learning. So for instance, this particular function is so important that it has a specific name. It is called the rectified linear unit. So you're using this as something called an activation function. So in machine learning, F is called ReLU, rectified linear unit. Okay. Let's look at another example and see an instance of scalar multiplication. You see, I gave you all these definitions, this abstract perspective, but the point is eventually to increase, to broaden our scope, and then zero in onto the concrete particulars again. So this is like a very particular, very specific thing that is very useful. It's just that our formalism so far, it wasn't developed enough to handle it. So I needed to mention it at the very least. So let's look at for instance, sine wave. Okay? So I can take trig functions certainly. Here's another example. Let's say that my function looks like this. Okay. It's easier to draw the boxes first. Okay, so okay, this is sine wave. Does this? So it oscillates between +1 and -1, and backwards as well. So this is 0. So this should be pi, 2 pi, 3 pi, and so on. And the height is 1. So this is 1, this is -1, this is pi, this is 2 pi, and so on. And this is minus pi. So f of t equals sine of t. Now, what is very important is to be able to change the amplitude, so to speak, of these waves. So this particular wave function is oscillating between 1 or -1. But it turns out that it is important to be able to work with wave functions that oscillate between, let's say, 3 and -3. So the amplitude is larger. So that is encoded, or that is related to this scalar multiplication. So let's say then 2 times f so let me write it like this. It's now 2. Okay, then so this was f. If I scale it by a factor of 2, now I'm stretching it in the y direction. That is to say, now I'm going to have oscillations, but it's going to move between 2 and -2. It goes this way, and I have. So this now is 2 times f. Okay? So let me put numbers here. So this is 1, 2, -1, -2. This is pi, as usual, 2 pi, and so on. This is minus pi. Does this make sense? Any questions about these two? So this is a valid vector space here's vector addition, here's scalar multiplication. The vectors are functions. So each vector has its own graph, looks like this, and I can do things like this. And of course, I can take linear combinations of functions. I can ask whether or not certain functions are linearly independent. Here's an example for that, for instance. Certainly, I can look at exponential functions. Let's say that I have f of t equals 1. This is just a constant function that is constantly 1. It's a constant signal, if you want. And g of t is t. My claim is that f and g are linearly independent. They are vectors. I'm telling you, I'm asking, or I'm claiming that they are linearly independent. The vectors f and g are linearly independent. Okay, so before we started with, so whenever the question was about whether or not certain things, a bunch of vectors were linearly independent, so we had vectors and we put them, so they have column matrices, we put them in a matrix and computed certain things. In this case, you can't quite do that. So that is why you need to use this axiomatic definition of linear independence. So how to do this? So say there are numbers real numbers a and b such that AF plus BG equals 0. If I can verify that A and B have to be 0, then I'm done. Now, how to use this? First of all, this is a vector, this is a vector, this is a number, this is a number. I scale multiply, and then I vector add. So the end result of this is a vector. I'm writing here 0, but I really mean the 0 function, the 0 vector inside my space. Okay? And what does this mean? This means that no matter what the input t is, a times f of t plus b times g of t equals 0. Okay, so if I fix a t, this is a number now, this is a number, this is a number, this is a number. So this is just a number, and this is a number as well. Let's open up the definitions. This just means that a plus 1 times 1 is just a, plus bx bt equals 0. Okay? Now I'm telling you that this equation, so a and b are such that this equation holds no matter what t is. That means that I can use certain values for t. So that equation holds no matter what t is. Plugging in, for instance, t equals 0, the equation tells me that a has to be 0. Okay? So really that equation says this: b of b times t equals 0 no matter what t is. But then I can plug in, for instance, t equals 1, which then would give me b equals 0. Gives me b equals 0. Okay, a has to be 0 and b has to be 0. Okay? And I started only with that linear combination. These two do tell me that a equals 0 and b equals 0. That is to say, if g are linearly independent.
So to clarify, it's linearly independent if A and B being 0 is the only way adding the two together
Yes.
gives you 0.
Yes.
Okay.
Yes. Yeah, certainly, if I were to start with some random vectors, take their linear combination like this, if I were to plug in a equals 0, b equals 0, this would certainly be 0. Now, if there are no other solutions for a and b that does this, then your vectors are called linearly independent. Okay? Now, it turns out that even in this more abstract setting, you can, at times, use vectors and rather matrices to handle this stuff. And that requires that one is able to use bases. But we're running out of time, so we're going to discuss that on Friday. And next week is going to be all about basis matters, both in the abstract setting or in the function spaces and so on, and in Rn. Okay, thank you. I'll see you on Friday. Okay, let's start. Good morning. So today we're going to keep working on this function space that we were discussing on Wednesday. But before going any further, I wanted to mention some of the many applications of linear algebra and why this abstract perspective is rather useful. Because in applications, as I mentioned earlier, whenever you encounter a vector space, often it's not in the shape Rn. It looks like something else, and then people realize, oh, you know, there's a vector space structure underneath. And so here is a zoo of a bunch of different cases. So let's start with the top one, for instance, Rn. That's our first example. Second example is, of course, the spaces of matrices. And we were also discussing the space of linear maps, linear transformations. Before, I was just using from Rn to Rm, but now that we have this abstract idea of a vector space, I can just as easily think about just the collection of all linear transformations from one vector space to another. Another way to come up with vector spaces is to take two of them and take their product. Right, this is sort of a split vector space, is what we had called, and this later evolves into either a direct sum or a tensor or Kronecker product. These are sort of important constructions that people use. For instance, people use this tensor product in the context of quantum mechanics when they're trying to talk about this entanglement of electrons. They're really using this tensor product construction. Then I can take any set whatsoever and a vector space, and I can think of the collection of all functions defined on my set taking values in this vector space. So maybe this S is sort of like a landscape, and your function, any function in this vector space, is giving you two values. One is pressure, for instance, and the other one is temperature. So this is allowing you to sort of compress all that stuff into one object and do certain transformations to it. Another big, very important example is sequence spaces. This is very important in the context of signal processing, and these are in particular called discrete time signals. And these are also very useful in the context of a field called cellular automata. We're going to spend some time discussing this case, some applications in signal processing. It's a beautiful field. We're going to spend 2 classes on this I guess, after the break. Then there is the space of power series. And the application of this is, of course, that if you have a time-dependent signal, discrete time-dependent signal, then you take something called the Z transform of it. You get a power series. And so it is, and you can also go back as well, and this is a very important thing to be able to do. It allows you to analyze properties of signals that you're getting in. That's sort of one of the important things you need to be able to do in the context of signal processing. Another thing is, of course, the space of differential operators. This is very important in anywhere, pretty much. Ordinary differential equations, partial differential equations, stochastic differential equations, when you have some sort of randomness. So whenever we're trying to model something, and that something is changing, that is, so using a differential equation, or in other words, using a differential operator is one of the important things. Spaces of polynomials, this we're going to spend time today on. Space of splines. Splines are almost like polynomials, but they're like piecewise polynomials. It's just a continuous function, but there are certain control points, let's say, and between those control points, these splines are like polynomials, but then maybe they have like corners and stuff. So this is very important. For instance, this is an abbreviation for continuous piecewise affine splines, and Bezier curves is a special example of this. When you're trying to do computer-assisted design, let's say you want to model, you want to design a certain font for, like typing things. This is, so splines is what people use. Another very important application nowadays is, of course, the spaces of neural networks. It's very important in neuroscience, theoretical neuroscience, especially. Also it is important in machine learning. So now people are looking into deep neural networks, and large language models is sort of like the name of the game nowadays, of course. And they are special cases of neural networks. And another thing is, so it's a vector space that you attach to things. It's called homology, and this turns out to be very important in something called topological data analysis. You take big data, and using this vector space that you attach to your point clouds, which is called homology, you're sort of like able to come up with a summary of what the data is telling you. All of these are very important, so this topological data analysis has been booming the last 10, 15 years. Even though the idea of homology is at least 100 years old, they were able to figure out how to adapt this idea of this abstract notion of homology to something very concrete, which is big data problems. And as you can imagine, pretty much all of these items, especially when it comes to applications, is its own field. Okay, I'm not trying to say that once you understand linear algebra, you'll be comfortable with all of these. Each of these fields use some vector space, but depending on the problem that they're trying to solve, and depending on the tools that are available to them, certain linear transformations are more important depending on the field. And so to understand what is important in a given context, you really need to take the class, or perhaps dedicate your life to that field. Okay, yeah.
Is the discrete time signals, is that with the Fourier transformation?
It is related, yes. Yeah. So you can imagine this. So this Z transform is something very similar to Fourier transforms. Yeah. Yeah. So this is. So there's a cousin to Fourier transforms. It's called the Laplace transform, and Z transform is the discrete version of it. Yeah. Yeah. Any other questions? Okay. So let's go back to a very special case, which is this. We were looking at a special case of this. Oh, before even going into that, let me give two more definitions. I mentioned how there was a corresponding notion to the null space of a matrix in the abstract setting, and likewise, there was another notion. There's another notion that corresponds to the column space in the abstract setting. Let me give those definitions. Let V, W be vector spaces. Vector spaces. And let me take, I guess, well, I can just use L. From V to W be a linear transformation. I can use T. Be a linear transformation. Its kernel is the analog of the null space, and its image or range is the analog of the column space. Okay. Then the kernel and image, aka range, of T are defined as follows. So before we were writing null of A or null of T, now we write ker of A or ker of T. Ker of T is the same thing as the set of all those vectors such that T sends V to the zero vector of W, whatever that zero vector is. It's a vector space, vector subspace of V. Recall this was a notation that I was using to denote that something here on the left side is a linear subspace of whatever is here. And the image of T is the analog of the column space, so I can write it like so. Let's write it like this. W in W such that there is a V in V such that T of V equals W. And so now this is a subspace of the target. Okay, let me also record it here. Kernel is the analog of null space. And image is the analog of the column space. Okay? You see, we're not using matrices, but certainly all of these make perfect sense still. So let's go back to this function space that we were looking into on Wednesday. So let me write it like this. Back to the vector space. Curly f is how I had denoted, and using this formalism over here, it's really standing for so f of RR, right? All the functions from the real numbers. So it's a space of single variable functions taking real values. So any vector, so recall, any vector in F is a single variable function taking real inputs and whose values are real, with real values. Okay? So first, I want to do two things in this class. First of all, I want to slowly start folding, let's say, the math that you've learned previously before coming to this class into linear algebra. And this really is the context for that. Okay? I want to sort of incorporate sort of college algebra material. For instance, trig functions. I want to think of it in terms of linear algebra. I want to think of also graph transforms or graph transformations in the context of linear algebra. And then I also want to talk about derivatives. I want to introduce a little bit calculus into this fold, into this discussion. So let's first start with graph transforms. Affine graph transforms. Let me start here. And by an affine graph transformation or graph transform, I really mean something like this. Okay, so you take a function and you can sketch its graph, and then you can shift that graph to the right by some units or to the left. Right? That's something that you learned in a previous class. So let's say, for instance, let's consider this. Take a function and give it back another function. Okay, let me denote this by, let's say, curly s. And I want this to happen. So if I feed a function, a vector f, to this curly s, what I want to happen is this. If this was f, now s of f is the same function, except it is shifted to the right by 1 unit. Okay, so. Okay. So I want this to be s of f. Okay, let me write it like this. Then the graph of h, it's a function, is the graph of f shifted to the right by 1 unit. The graph of f of h is the graph of f shifted to the right by 1 unit. So that's the description of this transformation. This transformation takes one function and gives you back another function. If you want to think of these functions as continuous time signals, this really is a time delay operator. Okay? You have a signal, and when you apply your shift transformation to your signal, what it does is that it delays the signal by 1 unit. Okay? Now, how can I be more explicit? So, okay, this is a nice description. But how can I be more explicit as to what this S does, really? So how can I write H in terms of F? Any ideas? Maybe I should give another example. So for instance, if I were to start with this function, let's say that originally my function looks like this. So here it's 0. And then immediately at time 0, it jumps to 1 and it stays at 1. So this is what is called the Heaviside function, or the unit step function. And I can write it like this, for instance. So this is 0. So f of t is 0 if t is less than 0. And otherwise it is 1 if t is positive or 0. Okay? So now if I apply my shift transformation to it, what's going to happen is this. So when I shift this to the right, instead of turning on, right, instead of becoming 1 at time 0, now it's going to become 1 at time 1. So now it's going to look like this. Okay? So this is now shifted f, shift by 1 unit. And if I wanted to explicitly write this, like I did over here, I would write it like so. S of f, right, at time t equals 0 or 1, depending on where time is coming from. So could you tell me what I should put here? Hmm? Yes, that is true. But I want to have an inequality.
If just t is less than 1.
Exactly. Right? If t is less than 1, I'm just looking at the shifted one, the signal is 0. And if t is more than or equal to 1, then the signal is 1. Okay? Does this make sense? So what I can write then is this, really. So how can I relate these two functions? In order to figure out what S of f is at time t, really, I'm looking at a certain value of f at a previous time. That is to say, S of f at 1, okay, really is f of 0. And likewise, for instance, S of f at 2 is what f is at time 1. And so based on this, now I can come up with an explicit description. I can write the shift like so. This is the same thing as f of t minus 1. Okay? So you see, I'm changing the input of f by 1 unit. I'm sort of subtracting 1 from t before applying f. And that corresponds to a certain shift transformation. How many of you have seen this stuff like this before? Okay. I have misjudged. I thought these type of matters were covered in previous classes, but okay. So now let's try to see if this is a linear transformation. Okay. So let me write it here. So note this. If I first take two vectors and add them up, okay, and I'm now looking at what is happening at time t, based on this definition that we were able to come up with, this is the same thing as f plus g. Recall that this is another vector now in my vector space, evaluated at t minus 1. Okay. But then, what is this? This is nothing but f of t minus 1 plus g of t minus 1. That's how you add two functions. But then note that this is nothing but s of f evaluated at t, and this is nothing but g of f evaluated at t. Sorry, s of g evaluated at t. And then again, I can combine these two, right? This is nothing but s of f plus s of g at t. And I didn't use anything specific about this t value, this input value, which means that s of f plus g is the same thing as s of f plus s of g. Okay? So shift operator is additive. We need to check one more thing for S to be a linear transformation, that is about the scalar multiplication of functions. And let's verify this super fast as well. S of c times f at t is c times f evaluated at t minus 1, which we know to be the same thing as c times f of t minus 1. But then I know that this is s of f. C times s of f at t, which is the same thing as c times s of f at t. And by the same reasoning, s of c times f is the same thing as c times s of f. Okay? So this means that this S transformation, this shift transformation, is a linear transformation on the vector space F. Okay? Because it respects how vectors are added in this vector space, and it respects how vectors are scalar multiplied. Okay? Now, it is also true that if you were to multiply two functions and then shift them, it will be the same thing as first shifting them and then multiplying. So S also respects function multiplication, but that is not the structure that we're looking into right now. Okay? These two properties do tell me that S is a linear transformation. thus S from F to F is a linear transformation. Any questions about this? Okay. Let me also note that there's nothing specific about this one, right? I could shift by 5 units, 15 units, pi units, whatever I want. Let's look at another example. Let me, for instance, look at another graph transformation. This is also very common to use. And this graph transformation, and I'm going to call it R, it reflects a function along the y-axis. Okay? So R takes a function, gives back another function, and it operates like so. If I have an f whose graph is something like this, for instance, I call that this function we discussed on Wednesday. It's a certain function, it's a certain vector in this vector space. When I apply R to it, its graph is flipped. So these are called affine graph transformations because, so there are some other versions as well, but the point is that these are transformations that are acting on functions, but the way they are originally described and the way you think about them is also like geometric. You're thinking of functions as the graphs of, as their graph, let's say, so that the functions are really shapes, and this transformation is taking this shape and doing something to it. So this is f, and this is R of f. Okay? So again, the claim is that this is a linear transformation from f to f. So there should be calculations like this that I did above. But in order for things like this to work, first I need to come up with a formula like this. I need to be able to say what is R of f at t in terms of what f is, in terms of what f does. So any guesses? R of f at t is something.
Negative f of t?
Well, if you were to do negative f, you would be flipping this way. You're close, though.
F of negative t? Then?
Exactly, yes. Right, because this makes sense. To understand, for instance, what this value is over here, let's say this is -1. Well, what do I need to do? I need to go back to the graph of f and see what it does to minus this input. So whatever is f of 1, right, this point, I'm going to put as R of f at -1. That is to say, this is the rule. Okay? Is this clear? Yes.
Is it worth thinking about it as a transformation of the plane or of the
Yeah, you can think of it that way. It's yes, but there's an issue with that, which is that the next stage, the next step would be to say, okay, I'm going to take any 2 by 2 matrix, and I'm going to see how it changes functions. But it turns out that not all 2 by 2 matrices turn out to be graph transformations like this. So it becomes more complicated. So for instance, think of it like this. If you had a function that is constant, its graph is horizontal. So a very straightforward 2 by 2 matrix is rotation by 90 degrees. You rotate by 90 degrees, now it's not a function anymore. But you want to end up with a function, so that's why it gets more complicated. It is useful to think that way in certain settings. It's just that it gets more technical. So we're leaving it like this. So any other questions about this? Okay. Again, let's verify that R is a linear transformation indeed. So perhaps I should be more explicit. I want to verify that R of f plus g is equal to R of f plus R of g. And I want to verify that R of c times f, c a constant, is the same thing as c times R of f. Okay, so these are question marks at this stage. So there's something that you end up needing to do in this setting. Because in this case, you cannot really sort of compute these expressions without referring to a function, without referring to an input. So it's sort of like slightly more complicated compared to linear transformations defined on Rn, where you have just numbers. In this case, you don't have numbers, so you need to plug in a certain input value and compare the input values of the left-hand side function and the right-hand side function, right? That's why here, for instance, I'm plugging in a t, and I'm verifying that, okay, so I have a function on the left-hand side, and I have a function on the right-hand side, and these two functions give me the same output for any t whatsoever. So that's what I'm verifying. So you're supposed to use a similar idea here. Let me just verify the first one. The other one is, I think I'm going to leave it to you. So what is this? Based on this formula that we came up with, this is nothing but f plus g evaluated at minus t. Which, of course, based on the definition of what it means to add two functions, this is nothing but f of minus t plus g of minus t, which then I can assemble back. Let me write it here. Okay? So you see, I started with the left-hand side function over here. I plugged in an arbitrary time value t, so this is now a number. And now I keep using the properties of the vector space that I'm dealing with. And I do a rearrangement, and I realize that this number, the value of r of f plus g, which is a function at time t, is the same thing as the value of this function at the same time. This is nothing but saying that this function is the same function as this function. Okay? And the verification of the second one is very similar to that. So I'm just going to skip that. Any questions about this? Okay. There's a phrase that is being used quite often, and that phrase is even function. Okay. Have you ever heard of this phrase, even function? What is an even function?
It flex across the y-axis.
Symmetrical value.
Yes, right? So a function, f of t, is an even function if its graph is symmetric along this axis. That is to say, if I were to reflect it, I would get back the same function. In this case, this doesn't happen. I get back a different shape. If its graph is symmetric along the y-axis. So here's an example. For instance, the absolute value function is an even function. Okay. So f of t, which is t in absolute value, is even. Right? Because its graph looks like this. Okay? Another example, any polynomial function of even degree, for instance, f of t equals x squared, t squared, even. And so this one looks like this. So it's a parabola. Cosine is also even. Right? Because this is a wave function that looks like this. Okay. So using a formula, then I can write it like so. F is even if f of t is the same thing as f of minus t. But then f of minus t is nothing but r of f at t. And so now you see I can think of what it means for a function to be even like this. I can abbreviate it like so. F is even if r of f equals f. You apply this r transformation to it. It's a linear transformation. And you get back the same thing. Okay? I can go further. I can take this to the other side and say, really, the function f on the left-hand side is I times f, or I applied to f. There's an identity transformation that doesn't do anything. And I can say like this. So f minus, or r of f minus f equals 0. And r minus identity transformation applied to f is 0. Okay, this is the same thing as saying that f is in the kernel of the linear transformation that is r minus I. Okay? Now, we discussed how the kernels of linear transformations, null spaces, are linear subspaces. And from this, I get that the collection of even functions is a linear subspace. Then the set, and I can write it like this: f sub even in F is a linear subspace. Okay? Any questions about this? So what do I mean by this? I mean that you can go ahead and verify if you wanted. If you were to start with two functions that are both even, and if you were to add them up, you would again get back an even function. Right? So for instance, if you were to add this and this, perhaps it's not that clear from the graph how that function would look like. Now, certainly you could draw it using a computer system, for instance. In any event, you don't need to do this. I'm saying that the sum of them, sum of this and this, is still going to be an even function. Okay? And really, all even functions are nothing but vectors in the kernel, that is to say, null space of this particular linear transformation. Right? Because I told you that the space of linear transformations between two vector spaces is also a vector space. So I'm doing that subtraction over there. Okay? Now, doing the same thing, I can apply the same reasoning, and I can get odd functions like that. Yes?
So, given that it's to go to the null space, why has there been a necessity to come up with another term, kernel?
It's just what other people use. Like in this context, people don't really use the word null space, because when you use something like the null space, it sounds like there's a matrix involved. Like, but what is the matrix of R? Right, that's an issue. Or like you could also use the word column space for the image or the range, but what is the column in this case? Right. So here's another example. A function is odd if f of minus t equals minus f of t. This still has some symmetry, but it's not quite like this. It's the symmetry when you reflect it and you get back minus the function. So here are examples. So for instance, t, just the diagonal, or any polynomial of odd degree, and that's why these are called odd, f of t equals t cubed, or sine function. So let me draw these. So that's my function in the first one. In the second one, it looks like this. In the third one, it looks like this. Okay? Certainly, if I were to take this, reflect it, I would now get this shape, which is nothing but this shape reflected this way. Okay? That's what it means for this to be odd. And if I were to reflect this along this, I get this shape. And if I were to reflect this along this, I would get this shape. Okay? So if the red one is f, the blue one is r of f. And just as I did over there, I can say this. F is odd is equivalent to saying that it's in the kernel of R plus identity this time. Okay? And consequently, the space of odd functions is also a linear subspace. Is a linear subspace of F. Okay? Now, it is not the case that given any function, it's either even or odd. It's more complicated than that. But in a sense, it is still important to be able to distinguish odd functions and even functions. It turns out that even though this function space F is a rather sophisticated space, as a caricature, I can think of it like this. Okay, so let's say that this is the caricature for F. Somehow this horizontal axis is similar to F even, and this vertical axis is similar to F odd. Okay, so this is a caricature. We're going to discuss what I mean by this caricature more on Monday, but I think since I'm running out of time, I don't want to continue any further. Okay, thank you. I'll see you on Monday.